Carrying capacity refers to the maximum population that environmental conditions can sustain in the long run. So if we're looking at carrying capacity, we're looking at what can be long-term sustainable. So I'll write it down again for you. So carrying capacity is the maximum population that an environmental condition can sustain in the long run. For example, carrying capacity. Maybe you have a patch of woods behind your house, and maybe there are 10 family of deer that live in the patch of woods. That could be the carrying capacity. Maybe if an 11th family of deer comes in, or 11th pair of deer, however you want to think about it, comes in, maybe there's not enough foliage, maybe there's not enough space, maybe there's not enough food and water and shelters to sustain that number of deer. So it surpassed the carrying capacity. But while there were just 10, it was okay because there were enough resources to sustain that population of deer. So that's a very elementary example, but it gives you an idea of what carrying capacity looks like. So over here we have a formula. And in this formula, I know M is usually slope, but in this formula, the M represents the carrying capacity. So be careful while you're looking at this one. And then the other things hold as they have been. So T is time. RK is a constant. And another one that you're going to want is A, and that is the carrying capacity minus P sub 0 all over P sub 0. And P sub 0 is our population at time equals 0. Those are the pieces of the formula we're going to want to know. So let's see what we're trying to do here. The number of mountain lions in a wildlife preserve is modeled by a P of T equals 1680 over all that, where T is the number of years after January 1st, 2010. Okay, so let's think about this for a second. What is the carrying capacity? What is the population on January 1st, 2010? So let's start with one thing at a time. We have our model. We have P of T is equal to 1680 divided by 1 plus 4.2 e to the negative 0.11 t. And that is just what we were given here for our population equation. So we have our population. We have all this initial information. So this first question is asking us to identify the carrying capacity. Well, the carrying capacity in our equation is this right here, because it's matching with our formula that we were given for P of T. So our carrying capacity, that's our M, and that's 1,680. Now this one is asking us also, what is the population on January 1st, 2010? Well, notice that this equation where T is the number of years after. So this means that this would be T equals 0. So if we replace T with 0, we'll have P of 0 equals 1680 over 1 plus 4.2 e to the negative 0.11 times 0. Well, 0 times negative 0.11 is going to be 0. Anything to the 0 power that's not 0 is 1. So any non-zero number to the 0 power, that gives us 1. So as we go to solve this down, this is going to look like 1680 over, this piece all goes to 1. So 1 plus 4.2 That'll give us 5.2. Which if you do that calculation and round to the nearest lion, we'll have 323 lions. There we go. So our initial population, our P of 0, was 323 lions. According to the model, what is the population after 15 years? So we need our population after 15 years. So that means that T is 15. So P of T, so P of 15 in this case, I'm using our population model that we have right here from the question. 1680 divided by 1 plus 4.2 e to negative 0.11 times, and this time our time is 15, so times 15. So be careful when you type this all in. I would calculate the bottom first, and then take the top and divide it by your calculation from the bottom. As you type it in, make sure you're getting 930 rounded to the nearest lions, but 930 lions. Let's try part C. What does the model predict that the mountain lion population will reach? We'll try that again. When does the model predict that the mountain lion population will reach 1,500? All right, so when are we going to reach 1,500? Well, that means that we're trying to find P of T to equal 1,500. And we want to know what T equals. So we need to find T. So that'll look like 1,500 equals 1680 divided by our 1 plus 4.2 e to the negative 0.11 t. So now we need to solve this down for t. Well, let's do a little bit of what I call switcherooing, which means we need to rearrange this equation, switch it around a little bit so we can solve for t. So if we multiply both sides by our denominator, so if we multiply this right here to both sides, and then we divide by our 1,500, we'll have t in the numerator, 1,500 will be over here. So let's try that. So that'll leave us with 1 plus 4.2 e to the negative 0.11 t equaling 1680 divided by 1,500. Well, at least now we have the t isolated on its own side. So let's do this division. This division works out to be 1.12. Okay, so now if we subtract 1 from both sides, so subtract 1, we'll be left with 4.2 e, the negative 0.11 t is equal to 0.12. So now let's divide both sides by the 4.2. I'm running out of room, so I'm going to continue over here. So what we'll be left with is our e, negative 0.11 t is equal to, and if you do this division right here, it works out to be 0.0286. We have to get the t out of the exponent. So the way we get the t out of the exponent is we use our natural log. The natural log and the e cancel, so we have negative 0.11 t is equal to, and if you write through, you can do all in one calculation. If you want to do your calculation for your natural log now, you can. I'm going to save it and do it all at once. So then t equals, and then if you divide the negative 0.11 and divide over here by the negative 0.11, it looks like we will get t is equal to approximately 32.31 years. There we go. So 32.31 years, we will expect the population of mountain lions to reach 1,500. It's still below the carrying capacity of 1,680, so it should still continue to grow. So now we're asked to compute and interpolate p prime of 12. So p prime of 12 means the rate of population growth after 12 years. So you can use the quotient rule or the product rule. Take your pick. I'd rather use the quotient rule. So I'm going to take my p of t equation, and instead of having the fraction, I'm going to use a negative exponent, which means it's going to take what was in the denominator of my fraction right here, and it's going to raise it to the numerator, and it's going to have a -1 as the exponent. So that will look like, there's the 1680 that was in the numerator. Now here's my former denominator, so 1 plus 4.2e negative 0.11t, and since I moved it to the numerator, I have to do my -1 for my exponent. So p prime of t says to bring down your power. So that will leave me with my 1680, my constant to the front, bring down my power, so -1, rewrite. And subtract 1. Well, it was -1. I subtract 1, that gives me -2. Now we have to use our chain rule. So our chain rule says to take our derivative of the inside piece. Well, the derivative of 1 is 0. The derivative of something raised to e to the t is, in this case, whoops, let me switch my color back. (4.2 e to the negative 0.11t). And since it is e to a function, we have to do our chain rule again. And that will give us our negative 0.11. There we go. All right, so there's our derivative. So now we need p prime of 12. I'm not even going to try to simplify that derivative. I'm just going to leave it just like that. So we are replacing all of the t's with 12. There we go. I think we got them all. And now be very careful when you go to type it all in. You can type it straight through on your calculator if you're using a scientific or a graphing calculator. If you're not using a scientific or a graphing calculator, be very careful as you type it all in. You should get p of 12 is about 46. So what does this mean? This means that in January of 2022, the population of mountain lions is increasing at a rate of 46 lions per year. So remember, we were looking at our population of p of 12, so 12 years later. So that would be January 2022. And our population is changing at a rate of 46. So this would be an increase of 46 lions per year.